Hello and welcome to another instructional video in this course. Today we are going to be looking at polyatomic ions. And if you remember, we have been talking about ions already. You should know that they are charged particles. They result because there are more electrons than protons or more protons than electrons. And therefore they're going to have a negative if there are more electrons than protons charge, or a positive charge if there are more protons than electrons. Well, in this case, we are going to be looking at polyatomic, meaning poly, many, atoms. So it's a group of atoms, and that group has a net positive number of electrons, meaning more electrons than protons, or has a net positive number of protons, meaning more protons than electrons. So the group is going to have a charge. Okay, it's going to have more electrons than protons, or more protons than electrons, and the whole group then is going to be a charged particle, not just a charged atom, but a charged particle, a group of atoms. So these are going to be named in a way that we need to recognize them. They're usually going to end in ATE or ITE in some cases. Not always, but that is one way that you can recognize a polyatomic ion. So we're going to be understanding these, recognizing them, and then using them in compounds. We're going to see that they can be the second part of an ionic compound. Okay? All right. In Model 1, we have types of ions, and this is the type that we talked about previously. Monatomic, one atom. So like nitride, remember the IDE ending with an ion, IDE with a monatomic ion. Here sulfide, chloride, and in this case nitride has a 3 negative, -3 charge. Why? Because it has 3 more electrons than the total number of protons that are in the nucleus. Sulfide is a 2 negative because it's got 2 more electrons that are surrounding the nucleus than there are protons that are in the nucleus. And chloride, -1, 1 more electron than the total number of protons. Down here we have polyatomic ions. The difference, you'll notice that there's a group, and there's a dashed circle or dashed oval around this group, which means there's a nitrogen and 3 oxygens that are bonded together, covalently bonded, by the way. We're going to talk about that in another video upcoming. They are bonded together. These are all non-metals, and they are bonded together, but collectively you'll notice that they have a charge on them. That means the total number of protons, if you'd count all the protons in all 4 nuclei and then count up all the electrons that are around the different nuclei in this group, you would have 1 more electron. The total number of electrons is 1 more than the total number of protons in this whole group. Thus, the group has a -1 charge. Here, this whole group has a 2 negative charge. That's not a 2 negative. It's not just for individual atoms. It's for the whole group, because we're counting now the total number of protons and total number of electrons in the whole group. Here we have 2 more electrons than the total number of protons. Here, ammonium has 1 more proton. Total number of protons in all of the 5 different nuclei of the 5 atoms that are there. The 5 nuclei, if you count up all the protons, the number of protons is 1 more than the total number of electrons in this particular molecule. Okay? Here's nitrite, sulfite, and hydroxide, and you can see that these all have charges as well for the same reason. They either have more electrons than protons, thus giving a negative charge, or in the case with ammonium, have more protons than electrons, giving it a positive charge. The only difference is poly. This group, they're all ions. All of these are ions. It's just this one now, polyatomic, which we're studying today, have several atoms together to make the whole group positive or negatively charged, and thus a polyatomic ion. Model 1. So, name of the ion, charge on the ion. We're going to be looking at these different particular ions here and figuring out what the type and number of the atoms is and the chemical formula. So let's just fill this in really quickly. Nitride, the charge of nitride is 3 negative. Usually written this way, 3 then negative. It's still the -3 charge on it. Sulfate, sulfate has a 2 negative, sulfite has a 2 negative, ammonium has a 1 plus, or just a plus, okay? And type and number of atoms. So type and number of atoms. So in this case, we just have nitrogen, and you've got 1. Nitrate has nitrogen, 1, and it's got 3 oxygen. Sulfate, 1 sulfur, 4 oxygens. 1 sulfur, 4 oxygens. Sulfite has 1 sulfur and 3 oxygens. And ammonium has 1 nitrogen and 4 hydrogens. 1 nitrogen and 4 hydrogens. The chemical formula is basically, in some cases, you just have to look at it's kind of given to you. You just have to look at the number of atoms and the type of atom, and then just make your formula. So in this case, chemical formula for nitride is just going to be N, and then a charge on it. So it's just N negative 3 or 3 negative. Chemical formula for nitrate. Nitrate, you've got 1 nitrogen. The central atom in this case is going to be written first. That's in the middle. So N, 3 O's, and a negative 1 charge. So NO3, and then a negative 1 charge. Sulfate. Sulfate's got S, 4 O's, as we've written here. So it's SO4 and a 2 negative charge. So you can see what we're doing here. We're just taking the number of atoms and the types of atoms and combining that with the charge to make the chemical formula for these polyatomic ions. NH4, but don't stop there. It is an ion, so we're going to put a +1 charge on it. Consider the terms monatomic and polyatomic as they're used in Model 1. Write a definition for each of these terms. It may be helpful to break the words apart, for example, poly and then atomic. And monatomic just means 1 atom. Polyatomic means 2 or more atoms. Okay? What type of elements, metals or nonmetals, are shown in the polyatomic ions in Model 1? So elements here, metals or nonmetals, are shown in the polyatomic ions. All of these, oxygen, nitrogen, sulfur, chlorine, there's sulfur, nitrogen, again, all of hydrogen, you got hydrogen here. All of those are non-metals. Okay? What type of bonds, ionic or covalent, hold the atoms together in polyatomic ions? Those would be called covalent. We haven't talked about that yet. Covalent just means co, it means with, and valent, that means the valence electrons. Those outermost electrons are being shared, one atom with another atom. So these are shared electrons, and that is what is bonding the atoms together. So in our polyatomic ions, this nitrogen and this oxygen are sharing electrons, and therefore the nitrogen is pulling on those electrons, the oxygen is pulling on those valence electrons, and therefore they are bonded together. Same thing here, there is a sharing going on of electrons. The oxygen and nitrogen over here are going to be bonded together as well. Here we've got electrons, those dots are going to represent electrons. Okay? Electrons are being shared between the sulfur and oxygen. Here we've got electrons being shared. Here we've got electrons being shared. And here we've got electrons being shared as well. That sharing of electrons is going to hold those two atoms together because they're both pulling and tugging on those shared electrons, and therefore are going to be kind of holding hands, or both holding the same electrons, if you will. Both holding the same electrons, and therefore they're going to be bonded together. The net charge on a sulfate ion is -2. Explain how this ion obtains its charge. Your answer should include the discussion of subatomic particles. As I've mentioned already, it has a -2 charge because there are 2 more electrons than number of protons. Okay? The dotted line around each polyatomic ion in Model 1 shows that the group of atoms has a charge. So the whole group has a charge. The charge is not any one atom, as I mentioned. but rather on the group of atoms as a whole. Based on your knowledge of monatomic ions, propose an explanation for the net charge on a polyatomic ion. Your answer should include a discussion again of subatomic particles. That just means, again, the polyatomic ion, you would just count up the total number of protons in all of the nuclei. Total number of protons is going to be either greater than or it's going to be less than total number of electrons. As a result, you're going to have a charge that results in a charge, positive or negative, and thus we have an ion. Okay? So, if the number of protons, the number of electrons, if they are equal, then you have a neutral compound. But that's not the case here. This compound is not neutral. It is going to be charged, and therefore we call it an ion. And in this case, if there's several atoms involved, that whole group is called a polyatomic ion. Similarities and differences between the nitrate and nitrite. Let's look back up here, nitrate and nitrite. Nitrate, here we go. Nitrate has nitrogen. They both have nitrogen, they both have oxygen, but one of them has one fewer oxygens. But they have the same charge. Okay? So same charge. By the way, we'll look at the structure of these polyatomic ions and kind of show you how these electrons might be distributed and why there is a charge that results here. Okay? And we'll look at that in an upcoming video. Same charge between nitrate and nitrite. They both have nitrogen, they both have oxygen, but what is the difference? The nitrite has just 2 oxygens, whereas the nitrate has 3. Okay? What are the similarities and differences between sulfate and sulfite? Similarly, not exactly the same, but you'll notice that sulfate has 4 oxygens, whereas sulfite has only 3. So the fite, it looks like the sulfite has 1 fewer than the sulfate, just like the nitrite has 1 fewer oxygens than the nitrate. So that might be a clue as far as the naming process in these polyatomic ions. But the similarities, they both have sulfur, they both have oxygen, they both have a charge of -2. It's just that the sulfate has 1 fewer oxygens. Okay? Alright. The chlorate polyatomic ion has a charge of -1 and is composed of 1 chlorine atom, the central atom, and 3 oxygens. So if I was to draw that, based upon the others, they're very similar. So chlorate is going to look like this, Cl in the middle, and I'm going to have then 3 oxygens. You might have a little overlapping there to show they're kind of bonded. Alright, there's oxygen, oxygen, and I'm going to put a dotted circle around this, or sometimes you might see them in a bracket like that. That's possible as well, but somehow you're going to show they're a group, and that group has a -1 charge on it. Sometimes you'll see a 1 negative, or sometimes just a dash for the negative symbol. Either one, it means -1. Okay? Write the chemical formula for chlorate, including this charge. So chlorate is going to be ClO3. We were told it has 1 chlorine and 3 oxygens and a charge of -1. So we got to put up here, the superscript has to be the -1 charge right there. Okay? In your group, discuss what chlorite would look like. If this is chlorate, chlorite we learned has always 1 fewer oxygens. There's not a set number of oxygens for the 8 or the ite. It's just that we always know the ite is always 1 fewer than the 8. Okay? So the ite here is going to look very similarly to the 8, but it's only going to have 2 oxygens. So we're going to have the chlorine and the oxygens are going to overlap here a little bit, forming our ite, and it has a charge, probably a similar charge, right, as the other ones. So ite here is going to be ClO2 with a negative charge. Write the chemical formula for chlorite. Oh, we just did that right there. We anticipated it. ClO2 with a negative. Here now what they're showing you in Model 2 is, hopefully you're familiar with the idea of polyatomic ions. Now they're just going to throw at you a whole bunch of different polyatomic ions so you can begin to become familiar with them and just recognize them a little bit better. So ammonium is one of the common positively charged polyatomic ions. And then here you got a whole bunch that are -1, some that are -2, and one that is -3. Okay? Question 11. What is the only polyatomic ion that is a cation? Cation, remember, is positive, and that would be your ammonium. How are bicarbonate and carbonate related? So let's find those two. Here's bicarbonate. Here's carbonate. The difference is they both have a CO3, but this one has the H there. And H as an ion would be a plus. So notice that this bicarbonate has a charge that is 1 greater than this carbonate, because that H there brings in a plus there as its ion charge. So it's bringing in an extra proton. H plus is basically just a proton. That's what it is. It's a hydrogen atom without its electron, and there's just one single proton in there. So that is the bi there is indicating that you've got the H plus bicarbonate. Predict the chemical formula and charge for the bisulfate. Well, if we've got bicarbonate has HCO3 with a -1 charge, then if we had sulfate, bisulfate, we would assume would be the same formula here, but just with an H at the front. SO4, H at the front, and that is going to increase the charge by 1 because of the H plus being added. So up here where sulfate is a -2, now it's going to be a -1. Chromate and dichromate. Here we've got chromate, dichromate. Dichromate is going to have the same elements but different ratio. So chromium and oxygen, chromium and oxygen, but the ratio is going to be different. So chromate and dichromate. Here we've got same elements, but a different ratio. Different ratio. So the chromate, the chromium and the oxygen are in a 1:4 ratio. Here the chromium and oxygen are in a 2:7 ratio. Okay? Number 15, bromine forms polyatomic ions with structures similar to those of chlorine. So bromine, chlorine. Using the chlorine family of polyatomic ions as a model, predict the name of the BrO4 with a -1 charge on it. So we're going to predict the name of this. So let's look back up at the one that has chlorine in it. Here we've got chlor, that's the kind of the root part of chlorine, ends in ATE. There's the chlor, ends in ITE. So chlorate, chlorite. We're going to just mimic those right there. We're basically going to copy those down, but replace the Cl with the Br. So this is BrO4 with a -1 charge. Here we've got a ClO3. Oh, here it is. Chlorate. Here's a ClO4 with a -1. That's called perchlorate. So that prefix PER indicates that it has one more oxygen than the chlorate. Alright? So this would be perbromate. Perbromate. Identify the polyatomic ion in each of these ionic compounds. Write out the name and formula of the ions, including their charges. So notice what we have here. We have an ionic compound. How do I know it's an ionic compound? Remember from a previous video, ionic compound is always going to have metal and then non-metal, or that non-metal may not be an individual non-metal element or atom, but it now might be also a polyatomic ion. Okay? So here we have metal. This is your, I'm going to circle the metals. Metal. They always come first, remember? They always come first. In this case, and we're going to talk about this little exception here in just a second, but in the first two examples, A and B, you've got metal, and now the second part here is not just a single nonmetal, but it is a group. So there's your carbonate. Here's your hydroxide. So this is your metal, and your nonmetal. Okay? Non-metal. Okay, here is a bit of an exception. There are always exceptions, right? Here's a bit of exception. Remember we talked about the one positively charged polyatomic ion up here, the one cation, this ammonium right there. That is a positively charged ion, and so it's going to behave like a metal. Even though it's not a metal, those are not metals, but it's going to behave like a metal. So this first part here is our cation. The second part is going to be your anion. So we have to begin to recognize those polyatomic ions. We have to recognize that it's not just N, it's not just H, it is an NH4 polyatomic ion bonded with the Cl chloride ion. Okay? Model 3, ternary ionic compounds. What does that mean? Well, if you look at the prefix here, that basically means 3 or more parts. All right, 3 or more, maybe 3 or more elements involved. So ternary ionic compounds are going to have multiple parts involved here. So you'll notice here we have not just a metal and a nonmetal, but we've got 3 or more elements involved. So we've got, in this one, we've got nitrogen, hydrogen, phosphorus, and oxygen. As is the case in all of these, we've got 3 or more elements involved in our ionic compound. If that's the case, you are guaranteed that there are polyatomic ions. Okay? If it's just 2 elements, sodium and chlorine, metal, nonmetal, that is a simple binary ionic compound. Binary, just 2 elements. But now we got ternary here, 3 or more. I'm telling you, you're going to see polyatomic ions now if you see 3 or more elements involved. So here we've got polyatomic ion, cation, and another polyatomic ion. There's your phosphate. Together, you're going to have 3 of these. You need 3 of those times 3. Why? Because it just has a positive 1 charge with every one of the phosphate, because it has a 3 negative charge. Remember, all of the ionic compounds, when they come together, have to form an overall 0 charge, an overall neutral compound. So in order to do that, they have to combine in a certain ratio so that the positives and negatives are going to 0 each other out. Notice that's why there's a 3 right here. This whole polyatomic ion is put into a group, and then there's a subscript of 3 outside that group to show you need 3 of the ammoniums and just 1 of the phosphates. Here's your barium. There's a metal, but now there's your polyatomic ion. Ammonium, cation polyatomic ion, sulfate, negatively charged, and anion polyatomic ion. All right. Again, all of these have to combine in a ratio so that you have a neutral atom. So positive 1 with a negative 2, I'm going to need 2 of the ammonium. Here's a plus 3 with a negative 2, I'm going to need 2 of the aluminum and 3 of the carbonate. All right, let's answer some of these questions. I probably have answered some of them already, but let's go through these so that you can check to see how you did. How are ternary ionic compounds in Model 3 different from binary ionic compounds that you've seen previously? So it just means that with ternary R there, you've got 3 or more elements. A binary, 2 elements involved, metal and non-metal. Consider the compound iron 3 hydroxide in Model 3. How many hydroxide ions are combined with the iron 3? Well, if we look at iron 3 and then hydroxide, we use the same exact process that we had before. You have to form a neutral compound. So this plus 3 has to be neutralized, not really neutralized, but combined with the same number of negatively charged ions in order to make a neutral compound. So I'm going to need 3 hydroxides for a total of -3 here to match the +3. So the formula is going to be Fe. Do not put any charges once you combine them together. It's now neutral. Don't put charges here. So Fe, and then in parentheses I'm going to put the OH because I need 3 of the whole group. Not just 3 of the O's, not just 3 of the H's, the whole group of hydroxide. I need 3 of those. In our answer, the only combination of iron 3 and hydroxide that should exist in nature. Yes, it is. This is the only one. This is the only possible combination. Because remember, we need a neutral compound. Okay? We need a neutral compound. Consider the compound barium nitrite in Model 3. Barium nitrite. What does the subscripted 2 inside the parentheses of the chemical formula tell you about the compound? So there are 2 2's here. So let's be careful. We have to make sure we know which one is telling us what. The subscripted 2 inside the parentheses is telling us that in this polyatomic ion, there are 2 oxygens bonded to a single nitrogen. Nitrogen bonded with 2 oxygens. That is the NO2. Okay? There's your metal. There's barium. Now, what does the 2 outside mean? It means I've got 2 of these particular nitrite polyatomic ions bonded or attracted to the barium. Okay? So this ion here that has a negative charge on it, this ion's got a negative charge, but the barium's got a 2+. That's why I've got 2 nitrates attracted to the single barium. And when they come together, they form this neutral compound that is written like this, with no charges written on them. This 2 inside is talking about the formula for the polyatomic ion. The 2 outside is telling me I have multiple polyatomic ions bonded to the single barium. How many atoms of each element are in one formula unit of ammonium phosphate? Well, let's look at this. It helps to draw. If you want to draw this out, by all means, or just write it down how many of each of these we have. This NH4, I've got NH4, but you see this 3 here? It's outside the parentheses. That tells me the whole group is triple. I've got actually 3 of these. And then the PO4, it's not in parentheses, so I just have a single PO4 group. Each ammonium is a +1. The phosphate is a 3 negative. That's why you need 3 ammoniums to match the -3 on the phosphate. So let's look here. I've got 3 nitrogens. I've got 3 times 4, 12 hydrogens. I've got 1 phosphorus, and I've got 4 oxygens. This 3 right here applies to everything inside. So I've got 3 nitrogens and 3 times 4 hydrogens. This 4, though, only applies to the oxygen because it's not outside of the parentheses. Student writes the chemical formula for an ionic compound, calcium hydroxide, as this right here. Write the chemical formula for each ion in the compound. So here's calcium. hydroxide is this, and when calcium forms an ion, it would be 2 plus. Hydroxide is an ion with a charge of -1. So why is this formula wrong? Because the proper formula should be 1 calcium with a 2 plus is going to combine with 2 hydroxides. Each has a -1. So I need to show that the hydroxide, all of the hydroxide, the entire group, is going to be doubled. Not just the H. This H right here has a 2 subscript. That tells me that just the H is doubled, not the oxygen. I need the whole group doubled. Okay? But don't write it as CaO2H2. That's something different. You need the OH as a group, and then the group is doubled. And it's a neutral compound. Many of the chemical formulas in Model 3 include parentheses. Which one of the following rules summarizes the appropriate use of parentheses in ternary ionic compounds? For the 3 rules that do not apply in all cases, show at least one counterexample for the chemical formulas. Okay, let's walk through these. Parentheses are used around any ion that is used more than once in a formula unit. Okay, what that says is if you have a formula unit and you are going to take and that whole ion, like OH negative, and if you're going to have multiple, let's say you've got, let's look at our example up here, calcium 2 plus. If you need multiple of these hydroxides, then yes, you have to write that in parentheses. Parentheses are used around any ion that is used more than once in a formula unit. This especially applies to polyatomic ions. Okay? Parentheses are used around any polyatomic ion. No, that's not true. You don't have to have it around a polyatomic ion if it's not showing up multiple times in the compound. So, for example, calcium calcium carbonate. I think carbonate is a -2, if I'm not mistaken. All right, carbonate -2. Calcium is a +2, so calcium carbonate. I just need 1 calcium, +2. I need 1 carbonate, the whole ion, which is a -2. I just need 1 of each of those. I don't need any parentheses there. Parentheses are used around any polyatomic ion used more than once in a formula unit. That is true. Okay? I think this case up here was talking about any ion. Well, obviously if I just have a monatomic ion, like calcium chloride, I don't put parentheses around the chloride. I don't need to because it's not a group. I just put a 2 there to show I have 2 chloride ions. Okay? But if it is a polyatomic ion, then yes, I definitely need to put it in parentheses and show that that group is staying together and it's being multiplied, it's being doubled or tripled or whatever. Parentheses are only used around polyatomic ions, anions used more than once in a formula unit. That's true, but it's not only for the anions. Remember, ammonium is a positively charged ion, and if that is combined with an anion that has a more than a -1 charge, then I'm going to need multiple ammoniums. So let's say this is combined with, well, let's just use my same example here of carbonate. Okay, carbonate has a 2 negative charge, so I'm going to need multiple ammoniums. So this is going to lead to NH4. I need 2 of them combined with the, I'm sorry, I did not need to put parentheses around the carbonate here. My apologies. So it's just NH4 doubled, so I'm putting that in parentheses, and then the carbonate. Okay? Write chemical formulas for the following ternary ionic compounds. All right, let's practice here. Calcium, sulfate. Calcium has a 2 plus, sulfate has a 2 negative. You can check me, you can scroll back up to the table that shows the different polyatomic ions, and you can check these values here. But calcium is a 2 negative, sulfate is a 2, sorry, calcium is a 2 positive, sulfate is a 2 negative, so I just need 1 of each. I don't need any parentheses. around the sulfate. Copper 2, so that's going to be a 2 plus. Nitrate is a -1. So nitrate, you can always refer to our table here. Here are, oh, this is the compounds. There we go, common polyatomic ions. Nitrate, here's our nitrate, -1. And the more you use these, the more that you'll become familiar with them, obviously, and pretty soon you'll have them memorized just by using them a lot. So I need 2 nitrates to match the 1 copper 2 plus. So this is going to be Cu, and then I got to put this in parentheses to keep the group together. Nitrate, NO3, and I need 2 of them. No charges on the compound. Lithium phosphate. Lithium is a +1. Phosphate is going to be a 3 negative. So I need 3 lithium. No parentheses around the lithium. Don't need it. It's not a group. It's just a single element. And then the phosphate, PO4. No parentheses around that. I just need 1 of those. Potassium is a +1. Permanganate. Let's double check here. Permanganate, I think. Here's our permanganate. It is a -1 as well. So this is manganese, O4. It's got the number of oxygens 1 more than the manganate. All right. So manganate would just be MnO3 with probably a -1 charge. Potassium permanganate. So it's going to be manganese O4 has a -1, potassium has a -1, so I just need 1 of each. This is my group. Here's my polyatomic ion, but I don't need to put it in parentheses because I don't need multiple of them. Here's my metal. +1 and -1, 1-to-1 ratio. Aluminum. Aluminum is a +3. Sulfite is a -2. So I'm going to need a combination here, ratio that's going to give me a neutral compound. Remember, one of the tricks here I mentioned earlier is that you just kind of cross these numbers, and that tells you how many of the other one you need. So aluminum is a +3. That tells me I'm going to need sulfite, and I'm going to need 3 of those in a group, parentheses around the whole group of SO3, and then a subscript outside that parentheses, so I need 3 of those. And then the aluminum, I'm going to need 2 of those, Al2. Okay? 2 aluminum gives me a charge of +6 total. 3 sulfite gives me a charge of 6 negative for a neutral compound. Magnesium, Mg, that is a +2. Bicarbonate, remember the bi here? We saw this earlier. It means you've got an H at the beginning. So bicarbonate, there we go. Bicarbonate right there, HCO3 with a -1 charge. This has a -1 charge, so notice the magnesium is +2, bicarbonate is -1. I'm going to need 2 of the whole group, put the whole thing in parentheses, and a 2 subscript outside that parentheses. Alright, let's move on, because now we're going to talk about ternary, and you've got 3 or more elements. Don't be intimidated by this. Just look for the groups that you're becoming more and more familiar with. Let's just kind of point out some of the groups first. Barium, there's a metal. So this must be a group, polyatomic ion. Here you got 4 elements. So we're going to be looking for 2 groups here. There's your group, there's your group. Here is potassium. We need to recognize that as a metal. So the rest of it is our polyatomic ion. Fe, there's your metal. So the rest of it is your polyatomic ion. Magnesium, metal. All of this is your polyatomic ion. Aluminum is your metal. There's your polyatomic ion. Let's name them. Barium, sulfate. You don't need to worry about any prefix or any way to tell the reader how many of each you are going to have, because it's the charges that determine how many of each you have and the ratio in which they need to combine. because barium sulfate is always BaSO4, always. There's no difference there. There's no other way to combine barium and sulfate. Here we have ammonium nitrate. Here we have potassium. This is dichromate. Here, now we come across iron, which, if you remember, has multiple options for its charge. How are we going to know which one it is? Well, we have to look at our table or know that this nitrate right there has a -1 charge. NO3 is nitrate with a -1 charge. And look how many we need. 3 of them. That must mean this is iron 3. So this would be iron 3 nitrate. Here, this is magnesium. And all of this right here, if you're not familiar with it, you look up at the table, but you'll become more and more comfortable with it. This is acetate. This is aluminum. It only has one possible charge, and that is a +3. And this is carbonate. This is carbonate. Carbonate has a negative charge on it. That's why you need 3 of these. The aluminum, oh sorry, carbonate has a 2 negative charge on it, my apologies. And that's why you need 3 of them to match the 2 aluminums. Each of the aluminums has a +3, okay? Let's dive into a little extracurricular questions here, some extension questions. If you were asked to go to the chemical storage area and retrieve a bottle of sulfate, could you do so? So, what they're saying is, can you just get sulfate? Well, sulfate is an ion, and you're not just going to be able to find basically solid sulfate, if you will. Sulfate is an ion, and it's going to be in a compound. So, for example, you might be able to get solid magnesium sulfate, or calcium sulfate. Or if you put this into water, you would have then magnesium sulfate, and we put a little AQ there to mean aqueous. It's dissolved, or it's ionized in water. It's put into water and made into a solution. Up here we might put S for solid. Okay? By the way, when you do put this into water, it is going to break apart. If it's soluble, it is going to break apart into ions. So this calcium is going to be surrounded by a bunch of water molecules. All right? These 2 ions are going to kind of be pulled apart by the polar water molecules, and you're going to have 2+ calcium ions and 2 negative sulfate ions kind of throughout the solution. You're not going to have the calcium and the sulfate bonded anymore, because they're going to be surrounded by polar water molecules that are going to pull them apart and distribute them throughout the solution. When asked to classify sodium acetate as either an ionic or covalent compound, the student responds, sodium acetate is both ionic and covalent. So explain why the student gave this answer. Well, they gave the answer because sodium forms a +1 ion. The acetate forms a -1 ion. So for this group, this acetate polyatomic ion, and for the cation metal, the metal cation, for them to stay together, be bonded, yes, it requires them to form an ionic bond, which means it is the charges, the opposite charges. It's called a Coulombic attraction. So the positive and negative charges are going to pull them together. But inside, if you look inside of this acetate, you've got carbon, hydrogen, or oxygen and oxygen. All of these nonmetals are going to be covalently bonded. We'll talk about covalent bonds a little bit later, but they are being bonded together because they're sharing. They are sharing electrons. Here, the sodium and the acetate, there's a transfer of electrons that happens which causes them to bond together. Okay? So ionic is transferring electrons, covalent is sharing electrons. All right, I hope that is helpful. This was all about polyatomic ions, and in our next videos, we're going to continue to talk about how we name certain things. We're going to be talking about naming acids, and we're going to be talking about naming covalently bonded compounds or molecular compounds. All right, I'll see you then.